Hello world, this is CS50 Explained, week 3 continued. My name is David Malin and we're here with our friend, Dan Armendariz.
Hey everyone.
Always a great beginning.
Yes. That's all we need. All right. I can start with that next time.
We could.
So what's happening today?
So today we pick up where we left off, focusing particularly on algorithms and less on code today. And we're actually going to integrate into this lecture one of your own ideas, as you may recall.
As I recall,
your one
an idea that
your
I
idea.
suggested we do not actually use in lecture.
Oh, you're being too hard on yourself. So these are exam books for those unfamiliar. They're used on campus for any written exams that classes might have. Why they're blue, why they're that size, and they have lines like this big, I've never understood. But what I wanted was an opportunity to put out in front of students 26 books, each of which has a student's name on it, A through Z, which I just simplify as A through Z, and to watch as a student sorts those books by a last name or by letter of the alphabet to see what would happen. So this too, we're kind of yielding control to an organic demo to see what happens. A lot of volunteers. I wonder what I gave. Oh, I got stress balls today. Maybe an elephant.
Yeah, last time I think it was your lunchbox full of stress balls.
All right, Mary Beth's our volunteer. This was also an opportunity for us to take a fancy new technology out for a spin, wireless videography.
Whoa.
So that Andrew could join us here.
He's
very discreetly hiding behind the TV.
One of the students, and they're coming in somewhat randomly at the end of a 3-hour.
I say randomly, but they're really sorted in advance. So I'm like, oh, gotta randomize.
Like this. Now your job in just a moment.
Look at that wireless fidelity.
So,
This is actually how they get tuned in at the end.
Wi-Fi, if you will.
Oh, Easter egg.
Now is going to be quite simply.
So is this live cut into the lecture?
Yes, I think I'm projecting Andrew now in the overhead so that students can
Whoa.
see what's going on.
Cool.
Now I'm projecting Andrew in the overhead.
There it is.
Pressure or anything.
And you
It's
make her do it one.
I know one-handed.
One-handed.
Sort these things
That's-
one-handed. We
You have
need
to
get
get the Britney Spears mic.
Yeah, we need to give her a wireless
Yeah,
mic
that's
that
no
she
good.
doesn't have to hold next time.
Yeah. I mean, this is
I don't know why I thought it would
big hindrance
be nice
here.
to time her so visually like that. Especially one-handed. This is really not a fair test.
Oh, there you go. You offloaded the mic.
So in the meantime,
So did
I
you get,
also didn't know how long this demo was going to take. Which is funny because you think I could just simulate it in advance.
did you get a sense of what style of sorting she was attempting?
Yeah, she was bucketizing here
Okay.
and putting some similar letters together, I believe.
in its place, you first move your
Looks like
hands around
sorting
the
by
A
bucket,
for
perhaps.
A for
Yeah,
B.
sorting by
You
bucket.
take a look at a pair of them side by side and just say, wait a minute, this isn't right, and then swap the order. We saw already on Monday that there's a number of ways in which we can do this. And
I believe what we were not doing was capturing the original feed from the wireless camera, so that's why we're not cutting full screen to the top-down view, but we did capture it from this angle. Oh, we did, actually. There we go.
One through smaller ones.
Now I know what's going on. Here's the answer to your question. She's made some.
I'm ordering them when I find two letters that I know are together in the sequence. I put them together so that I don't have to worry about keeping track of a whole row.
So I was just
Wait,
told.
wait.
Yeah, I just got
I'm
a
being
thing.
told too.
Yeah,
Yeah, you guys think in your ear too?
yeah, exactly. Yeah. The thing in my ear says that this was not, in fact, a wireless camera. Like
No,
you
it's
just
not
said.
the wireless fidelity. It's
So
the
when-
wired fidelity.
So when are
the
you?
wired fi.
So it continues to be Wi-Fi, which is great.
But he's walking around. So what it is, we found a really long cable online. And
So we're like 5 minutes into this episode, and I think you haven't said anything true quite yet.
no, the point here is look how slowly, look how long it takes to sort 26 letters.
nice like deflection there.
Right, the record to beat would have been 1 minute and 50 or so seconds.
Are you wearing the same thing now?
Very, very. I
That-
thought
that
that'd be a
is-
nice tie-in.
That is awkward. That's
No,
not.
I
That's
had
not
to-
a tie-in.
I had to
That's
prepare.
that's a lack of diversity in clothing right there.
Okay, so starting at the top and the bottom, and then working your
So
way
there's a little like
Okay, so
camera movement here, a little zoom in.
bubble sword, but
It would be hilarious, I think, if we did this more sort of like sitcom or reality TV style, where when students ask you a hard question or when you mess up, there's like a zoom right to your face when you're like have an awkward look.
Or
That would
maybe
be great.
we could do some office-style Jim remarks like,
Yeah.
Four quads, if you will, and then somehow merge them in the end.
Every week you have a
Consider
new
ultimately
plastic
how
bottle.
else we might do
I moved to smart water and
No,
week
you gotta,
3
you
continued.
gotta use reusable
Though I think we
containers.
took
It's so wasteful. So wasteful.
We took the label off so as not to endorse one water
you
product over
just-
another. But it's
you
an
just talked about it.
ridiculously sticky bottle. Oh, I did. Yeah, now I guess we're talking about it.
Yep.
Smart water. Don't take the label off because it gets very sticky.
CS50 brought to you by Smart Water.
and then 6 and 8 on each iteration.
It's a nice bottle. It's a little bigger than like the Poland
Just-
Spring or the generic ones. It looks nice.
No
It's a
disposable
nice
bottles.
Easter egg when it says Smart Water.
No, it's not an Easter egg. Just get a nice reusable bottle. You should just get CS50 Nalgene's or something. Just some sort of like.
We have
nice-
CS50 water bottles.
Then
Up to the right, you're not going to have 8 comparisons because you can't compare an element against
I need my Smart Water.
saw it on CS50 Explained. David shrugs at the environment.
Oh my god. Not the takeaway. Cut.
actually was and try to give ourselves a vocabulary with which to critique algorithms like this and soon our own. So the first pass through bubble sort, the first time I walked from left to right.
But this, what was happening earlier, I was asking the audience, what would be their own approach to this problem? Like Mary Beth sorting the 26 letters of the alphabet. And there too, you never know really what you're going to get. And there's not necessarily a right answer, because certainly you could get to the same result any number of ways. But that's one of the points today, to talk about the efficiency thereof.
Steps the first time, but then what happened after that? What's the one upside of one pass through an otherwise unsorted list? What can you tell me about the
So
algorithm
you're going into detail about which algorithm here?
Yeah. That was the biggest
Right
element.
now?
Number 8, even though she started
We got to stop
here,
talking over the
and
lecture.
every time I compared her against a neighbor, she kept
Oh, I think it was bubble.
right
Oh, bubble sort.
side of the list, and indeed that's where the algorithm gets its
Okay.
name. Now, by that logic,
And I try not to dwell too much on
need I make on the second
mathematics, at least very early in the semester, so as to have not to have students who think of themselves as I'm not good at math. I don't want them to necessarily make that leap to now thinking I'm not good at computer science, because it certainly
steps, where again, n
is not necessarily that implication. And in many cases, they're being way too hard on themselves when it comes to math.
end of this algorithm, presumably
But what we're trying to do now is to actually put some numbers, or at least symbolically some formulas around
one and two,
the cost of sorting something.
one final comparison.
And this is going to lead us ultimately to a discussion of asymptotic running times and big O notation and omega and theta.
If you recall from high school, frankly, a lot of
So we're at least generalizing away from the specific number of pages or persons or numbers to at least using n now.
this ultimately added up to in the general case if you have a variable like n, and indeed this one, if you looked at your old school math book,
This is the one leap I asked them to make is, as you may know from a lot of textbooks, at least in the US, they tend to have, for math books or physics books and the like, they tend to have sort of a formulas, reference sheet of formulas at the front and the back of the book. And so this is what
multiply this out, so that's n squared minus n
that summation works out to be.
2. No, it's really n squared
Now I'm
divided
just
by
doing
2
some
minus n over 2.
algebraic
So that's all
manipulation
nice
here to
and
clean things
interesting.
up.
But what happens
It's funny how
when
you
plug in a
skipped
value?
over the
Suppose I didn't have 8 people, but say a
perhaps the
million.
hardest
A
step,
million
Which is what?
pretty big number. Let's plug
going
that
from
in.
that summation to that.
Well, that's why I borrow the back of the textbook thing. I don't want to get bogged down into a detail like that when really what we care about is the end result. But I want to at least hold their hand through some of that. So now I picked an arbitrarily large example, 1,000 as input, just because I want to give them an appreciable sense of the
Million?
effect of that squaring.
A million, I think, right?
Was it a million? Okay.
499
Yeah,
billion,
A million squared, sorry, yes.
500,000 steps.
So what I'm trying to make clear here is that the n squared divided by 2 really dominates the n divided by 2. And so it feels reasonable at this scale, is my message, to just ignore that lower order term.
This algorithm kind of feels worse and worse, or you really start to feel the pain of that exponentiation, that n squared, which adds up pretty fast. And this detail
Hoping to
is
give them
lost on
intuitive, sort of
people. In fact,
get them to agree with me intuitively,
a certain senator
even though we're not really getting into the formal details ultimately of something like big O and its mathematical definition.
question, much like we're exploring today. Let's take a look.
This is fun. Now that we have the vocabulary bubble sort, now that it's been a couple days since it was first introduced, this is rather apropos.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president, and you're going through the rigors now. It's also hard to get a job at Google. We
So was
have
this
questions.
before
and we
Obama
ask
was
our
president?
candidates.
Correct. He was
During his
running, I
running?
think, running for president at this
I
time, and
see.
he's being interviewed by Eric Schmidt of Google
Okay.
at Google's campus, I think.
You guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
That too is probably why I chose a million.
Well,
It's a big lead into this joke.
I'm sorry, maybe we should do that.
I think the bubble sort would be the wrong way to go.
I think that was very well delivered.
Who told him this? I didn't see computer science.
We've got our spies in there.
Oh boy.
Who knew? All these years later.
Oh boy.
Ooh, CS50 Explained politically
Yeah.
charged.
isn't going to be all that useful. It is not a life.
Interesting foreshadow, though, of recent tech news.
Take as many as 500 billion steps. You can't really generalize too effectively from that and make good design decisions when writing programs. So let's focus, though, on how we might simplify this.
But I love when we're able to find little current events or fun video clips like that we can kind of weave into the lecture, because I think it punctuates it nicely and kind of spices it up and gives people a chance to like take another deep breath and dive back in.
N divided by 2. And the claim I'm going to make now is who the heck cares if you subtract off a little old n.
I mean, look, how could you disagree with me when I make these faces? Come on.
Should go back to Eric Schmidt. And
So if you use the right tone and the right face, everyone's going to believe you.
oh boy. CS50 exposed.
999,500,000? Not really. And so what we're going to do as computer scientists is ignore those lower order terms.
This isn't
Something like this.
more of a technical implementation detail, but I still bring printouts on slides, printouts of the slides on paper, which is really a stupid software constraint whereby with Keynote, as you might know, you can full screen your slides, and then on your laptop screen you can still see a sort of slide sorter, and you can see what's coming next, and you can see the presenter notes. But when you do that and you put your computer into non-mirrored mode, where you actually have two displays, it really gets in the way for us of then changing to like a browser window or to the CS50 appliance or any number of other tools, because instead I can't just swipe left or right and change spaces, because I'd instead have to like move a window onto the secondary display, which is the projector screen. And so presenter mode, so to speak, in Keynote just does not work well for a computer science class, which is why I just resort to printouts instead. So that I'm mirroring what you see on the overhead is exactly what I see on my laptop. I don't get to see ahead or see any notes to myself, which is unfortunate.
Asymptotic notation that we just use as computer scientists.
So here's Big O, and this is one of the more sophisticated topics, certainly, that we introduce in CS50. It's a topic assumed by some of Harvard's higher level classes, and so it's good that they see it early on. And I also think it allows us to have fairly sophisticated conversations about the running time of algorithms and asking students to assess one algorithm to compare two algorithms without necessarily looking at actual real wall clock running times. And yet later in the semester, as you know, with our misspellings problems that where students implement their own hash table or try or some other data structure to implement a super fast spell checker, then we flip this around and we worry a lot less about the theoretical differences among these data structures and algorithms and look at the wall clock time and really try to minimize that.
Of bubble sorts. In other words, if you wanted to claim that there's this upper limit on how many steps an algorithm might take, it's going to be in the big O of n squared in this case, the upper bound. What if I instead change?
And this is a subtlety, but I've been deliberately making sure I get better and better at this, because it's a touchy subject, because we simplify these definitions. We don't get into the formal definitions of big O and omega, but I take great care, and hopefully I did the same this past fall, to describe it as an upper bound for big O and a lower bound for omega, and not, as is commonly misused, a worst case and a best case scenario. Since indeed you can talk about an upper bound on the best case or on the worst case or on the average case, and you can talk about a lower bound on the same. And so too often, even within the class's sections and office hours, I think, do we as a class miscommunicate that big O is worst case and omega is best case, when really and formally they're upper bounds and lower bounds, so they're entirely contextually sensitive. However, with that said, what we do deliberately do on an exam, for instance, or when talking with students about this is generally talk about the upper bound, and we assume the worst case for that description because that's the interesting one. And when we talk about a lower bound on an algorithm, we assume that the lower bound is going to be driven by the best case. And so there is this sort of implicit conflation, but we try never to do that formally because indeed there is a distinction there. And we don't want them graduating from the course misinformed.
Seems like an important enough point to actually discuss in class. Do you actually explicitly mention that here?
I might. I forget if I do in this lecture, but the topic comes up again and again, and you might very well. I don't think I mentioned that point. I think I tragically explain it to you, but not to the class.
Virtual doors on the board, or when Sean was searching for something, if he had used binary search, log n would be the upper bound on how much time that takes. But those algorithms that ran in log n assumed what key detail? That the list was sorted, right? Your algorithm is wrong if your input is not sorted, and yet you're using something like binary search.
But this is a good example of something that's been tough, especially as the class gets larger and you have more teachers involved in it, teaching fellows, myself, course assistants, in that if I misspeak one year, honestly, or if I sort of teach something poorly one year, there's this unfortunate ripple effect that's hard to fix, even though we have weekly staff meetings and staff trainings, both during the term and at the start of the term. It's definitely been the case that I have made changes or improvements, I hope, to the course over the years, but it takes a while for them really to roll out because many of our own staff, and most of our own staff, has taken CS50 a year or two or three prior, and so they were sort of reared on one way of explaining things, or God forbid, an even incorrect way of explaining things early on. So change is hard for that reason, but we do try to at least mitigate it with training and staff meetings.
In C code. Choose like the bracket 0 notation. Bam, you're there. And indeed, arrays, as an aside, support something generally known as random access memory, because you can literally jump to any one place. We can do this even more simply. We can rewind to week 0 when we did Scratch. How much time does it take for the say block in Scratch to execute?
This isn't quite fair, I think.
Constant time, right? Say something. Say something. It doesn't
It's not
matter
bad, but then a student at one point, I forget if it was this lecture or another, pointed out, well, isn't it somehow dependent on the length of the string? Right? In theory, you got to iterate over that to actually display it on the screen, and that's completely fair. So I don't really love that idea anymore.
Almost best case potentially.
But in general, we've described statements as the primitives in Scratch, a statement as being constant time. It just does something.
What's an algorithm that
And printf too, and actually that's probably the context in which I regret saying, like, printf is just constant, print something on the screen. There too, in reality, you might very well have to iterate over something.
Right.
bubble sort takes you minimally.
So sometimes the abstraction lends itself to a discussion, a point I want to make, but other times if you dig down below that abstraction, you realize that's probably not the best thing to say.
Exactly. In the best possible scenario of bubble sort, in a lot of algorithms, if I hand you 8 people who are already sorted, it would be foolish for you, the algorithm,
Well, actually,
to
the
back and
abstraction
forth more
could
than once, right? 'Cause as soon as you walk
could make a big
once,
difference,
you
like
should
in
realize,
the
I made no
I think
swaps,
from
this list is sorted,
the
exit.
previous
But that's going to take you n steps.
lecture,
And
you had an
bubble sort is
example
another way
where
of
you
thinking
were
about it. Bubble
iterating
sort
over a string,
is an
basically,
omega, so to
and
speak.
the code, the for loop included remembering the length of the string in a variable that you defined before the loop, essentially, as opposed to putting the loop, as opposed to having the evaluation of the length that occurs every time the loop runs, which would change that loop from O of n to O of n squared.
Yeah, that's true.
Which was intentional in lecture, but that abstraction, pulling the length out, you don't know necessarily unless you happen to know the underlying details about how that length is actually computed.
And it might actually be fun to bring something like that back in at this point. Like, think back 2 weeks. Why did we rewrite this loop as this? That's a good example. We should do that next time.
But did you mention, you might have mentioned why you did that with the length.
Oh, I do intuitively, but now we have a way of expressing the actual impact, the algorithmic impact, that is indeed now just n and not just n squared, because you're asking for the length again and again. Or not n squared, but n times m, where m is the length of the string.
Technically have length. So if we now want to pick on you, if you don't mind, technically we could argue that printf does take a variable length input.
There we go.
And surely it might take more time to print a string this long than this long. So what if we consider just the sorting and searching examples? What about Mike Smith in the phone book?
So that was me regretting using printf as the example, but we can recover by focusing on something like the comparison or a swap, assuming we do have random access.
One step, maybe 2 steps, but a constant number of steps if I got lucky. And frankly, we saw on Monday your classmate get quite
And this slide brings to mind too.
Well, actually, wouldn't a comparison also depends on the type of data that you're comparing.
Well, I'm assuming it's a primitive, so you're doing it in a register and just comparing two values.
But that's an important assumption to tell.
Okay, true, because if we're doing strings, but even then, if you assume there's an upper bound on the length of a string and it's k, even if k is large, it's still constant. So I would worry we get a little too much in the weeds there. So I'm more comfortable, especially since we've talked about sorting, well, numbers mostly, though we did have the alphabetical letters, but even those were single chars. I'm not sure I would, at this point in the conversation, start peeling back the layers of a string and talking about its comparisons.
smallest number. So how many
This is deliberate as an aside. We've not really focused on what content we tend in CS50 to put up on the slides, but the minimalism here I think is representative of a pattern where I've definitely avoided deliberately, like philosophically, the very common style of having very long and detailed bulleted lists, which serve as a wonderful resource undoubtedly for students, so much so that they can often supplant the actual verbal expression of the lecture. But what I prefer in lecture is to use the visuals both for myself for talking points, to sort of know that this is essentially bullets and an outline for myself, but also they're meant to punctuate the lectures visually for students to know that right now we're talking about like a lower bound of constant time or upper bound of linear time, and to kind of structure the lecture in that way. And then we have CS50's notes, which one of the teaching fellows generally transcribes after the fact, which are much richer than I think my own slides would be because they capture exactly what happened in class, Q&A and all. So they're a much more accurate representation. But that's a deliberate pedagogical decision.
And squared y.
And if I do have presenter notes to myself, so to speak, in the slides, that's because sometimes a minimalist slide is not sufficient detail to remind me, why is this here?
Optimization in there that might let me abort after just n or so steps. So indeed, selection sort, omega of n squared. What about insertion sort, where I took who I was given, and then I plopped him or her in the right place?
And this, I like this too, to your question last time, why bother with people when it takes a little longer to do the algorithm and you have a nice graphical visualization? I think it's more compelling and it feels more natural for me to be talking about, remember that demo last time where your friends came up on stage and were moving around in this way? Feels a lot more compelling than remember that red block example we had on the overhead the other day that was one of several. It just feels a little more real to me to do it this way.
That was an operation. So if there were
And
three
referring to
people
their
here,
feet and like standing where they were standing.
on a long stage
I
like
think this is more compelling.
He or she could just go to the very end. But if we're thinking about a computer and an array of memory,
Or even better would be to just show them again the animation so that they could truly remember what was happening rather than.
So that is true. And I want to get better at that, actually having more visuals in class so that we can just do a quick toss to either the big screen or the big overhead projector for exactly that. And to be honest, to some extent, it's a software problem. Like, I could absolutely futz around, find that clip, and I can certainly come prepared with it. But weaving it into a conversation, it's just, I've never found a good tool for doing exactly that without students seeing me futz on the screen, or that still allows me to jump around, right? I could certainly embed it into the slides, but then I have to follow a script.
You have to do it TV style where the staff in the back are frantically trying to get the clip up of the thing that you were talking about.
Or like a radio show and you want a funny sound to accompany it.
Yeah, exactly. Push a big red button.
So here's your big moment. So Dan came to us from Berkeley, where he suggested that we introduce some playing cards as an opportunity with which to sort values. And we did exactly that. In fact, if you Google like huge playing cards on Amazon, you can find huge playing cards. And so we found a couple decks here.
Nice to meet you.
There's a couple of things about this
Story that are inaccurate?
Maybe. But there's a couple of things about this example that I think make it really good that might be lost in your implementation.
And tell me more.
Well, this is actually the first time that I'm seeing it, so this is going to be.
Oh, we
very
took your
interesting.
idea and made it so much better.
Really?
We did.
Didn't you just tell me before
No, we
we
have
started
much bigger-
rolling that I don't think it worked out well?
We have much bigger cards.
On the screen here.
Then what?
I don't know why I kept timing people. We don't do anything with this information.
This is actually, the timing is an important part of the actual demonstration. That I was. Those
You
are
didn't mention that
enormous.
over the summer when we talked about this.
Those
Oh, like Alice in Wonderland cards.
We're gonna keep it real this time, so we're gonna.
How are they going to be able to shuffle those? Or
Tedious quickly. If you could proceed to sort
so normally what you do is you have a class that isn't 800 people first
Yeah.
of all.
Okay. Gotcha.
And you get enough playing cards that you have essentially a deck for, if not every student in the class, then every 4 students in the class. Would be.
each doing it, how you might describe
I guess you really want every student.
Let me
in the class.
stipulate that your example has to be made to work with 800 students.
But this is the point, that this is the big, asterisk at the end of this example, in that it's kind of difficult to get it to work for 800 students. But anyway, what you do is you have a deck for every student in the class. You start out by giving 1 deck to every student in the class, and or actually better is you have 1 deck for every other student in the class,
Actually, better it is.
and then you give 1 deck out to every other student, and then you have the other student time student A, and in trying to sort it in whatever method they want, and then you swap, and then student A times student B as student B tries to sort them.
Okay.
And this takes generally like 2 minutes maybe or so for a student to be able to do. And you ask the students for the fastest time, and then you write that down on the board for 1 student. Then you ask students to pair up. So student A and student B are now in a pair, and you ask them to parallelize this task, and amongst themselves to figure out what might be the best way to actually sort it. And then you do that again, and then so you now have 2 pairs of students, and 1 pair will actually do the sort, and the other pair will time them. You swap and then try that again, and then you ask for the fastest time. And generally what you find is, unless you have some student that's just really, really good at cards and did a very terrible job at shuffling, that you will generally get about half the time. And then you do it again, but with 4 students this time.
Half the time. Half the time.
And you have the time yet again, and good teams will get down into the low 30 seconds actually to do it, which is fantastic. But it's a great way of getting them to think about how they can do it though. But it's a
So
great way
I
to
hear what
have
you're
them.
saying, but the first time you said this, I only heard playing cards, and I just ran
Yeah,
with
I
it.
know.
Jumbo
I know.
cards.
I know. Yeah.
But
this
let's
is
pull this back in.
important.
This would be a good, compelling opportunity for section, right? Where you do
Right.
have 10 students, 20 students, or a relatively small number of students.
Right. But it's also a good way to get them to talk about and think about algorithmically how they were able to divide and conquer the.
Okay. But in fairness, you need to make the distinction that they're now bringing multiple brains to bear
Right.
and
Well,
true
generally this is,
parallelization.
right. And so this generally helps in the discussion of parallelism and talking about the overhead that's involved with that. Like, sure, in many cases when you start pairing students up into groups of 2 or 4, you do see the times approximately half, but not exactly. It's like not quite as good. So you can talk about the overhead that's involved with that. So
So I think as a section demo, it's great.
yeah.
And
Not
actually
as
would
a
be,
mid
it doesn't need to
lecture.
even replace this. It's a nice, more in-depth add-on, I would say. But for a demonstration involving jumbo playing cards, come on.
Yeah,
It doesn't get better than this.
You just wanted the jumbo playing cards. I know, but it's fine.
Was there more to your idea than that?
No, just
No, I
one of the
agree. I
things,
agree.
Just
I agree.
one of the things. There's actually a variety of these sorts of ideas on the website CS Unplugged. I think it's csunplugged.org, but maybe not. Maybe Google that. And there's a bunch of cool
CSUnplugged.org has a lot of good.
demos
handouts
like that.
and-
And I think one of them, in fact, might be this card sorting or related to this card sorting.
Well, I think we should do that then with sections this fall. Actually, equip the team with some playing cards, normal sizes. I think is fine, and do exactly that.
Where do I have an algorithm with which I can search for someone like Mike Smith? Well, it's staring us in the face.
So
I can
what
literally
was
use
the
exact same program,
takeaway from the
effectively going up to the top
asking
again
students to
and
sort the
So
huge playing cards?
my goal of the playing cards was to begin to was really to have an opportunity to again solve a problem. How do you go about sorting this particular data set. It's a little more complex than our pure linearity of last time because it's not just a list of numbers, it's not just a list of letters. You actually have 2 layers to it, right? You have the suits, and then you have the numbers therein. So it was an opportunity really just to recap the kind of conversation we had last week and to think about it again. So it doesn't necessarily even belong in this day, but really in this week. It was for lack of time, perhaps, that we didn't do it the previous time.
I think next time, I'm not sure that you would want to spend the time in section necessarily to this.
Really?
But instead, because you spend a lot of time just sorting cards, you'll easily lose half an hour, 45 minutes
Really?
just to the students kind of
Even if
playing
it just
with
takes
cards.
2 minutes here, a couple minutes here?
There's a lot of organizational overhead.
Okay, but
getting
you
the
could
students
maybe
in.
have, not everyone do it, but you could have 2 students, 4 students come up in the front and then guide it a little more.
That's my point here, is that in the future you might want to have 2 tables, 2 groups of 2 basically, where they have the same task and actually sort of compete them against each other.
Competition would be nice. Okay.
And because most likely they will select different methods of sorting. Like one of them will
like
probably
that.
do some sort of like insertion sort or something, and then you can talk about the differences there. Obviously this moves away a little bit from the discussion of Big O because this is wall clock time rather than
Yeah.
algorithmic time since we have the same end.
But maybe if we did something like this earlier to motivate a discussion of sorting, it could fit well there. But I think key is using the jumbo playing cards.
I don't know if that's key, but I know how you like your jumbo playing cards. Are those
wonder
really the
what-
biggest ones you could? You can't find
I mean,
something like
that was big.
half person height,
That would be amazing.
3 foot tall sort of playing cards.
I wonder what the our volunteers have since done with those cards. Somewhere there's a group of really large students playing cards. No? Okay.
probably threw
No,
them out.
no laughs?
They threw it out.
All right.
No, they wouldn't.
How about you 3 and you 4?
They wouldn't until the end of the semester. Then when they had to move out of their
Yeah, they want to
rooms,
store
and you
that
got
for the summer.
purge. Yeah.
Let's do 7, 8. Come on up.
The volunteerism is still pretty strong here. Give away some playing cards, some stress balls.
Minus 8. There we go. Plus 1. Excellent.
I
All
don't know
right,
what
come
just
on up.
happened.
Let's quickly give you
What
numbers.
did-
It's always awkward if you need like 8 volunteers and like 9 people show up.
Number 4. Number 5.
What is the demo here?
So now we're going to start talking about sorting again
So go ahead if you could.
of
and let's
just
sort
8 elements
the
in this case.
original order that we had yesterday, which looked like this, if you wouldn't mind. And let's do it in front of
With
the
the table in the way.
All right.
We'll get in front of the
so
table.
merge
Yeah.
sort. This is where it's going to get kind of interesting because I seem to be giving myself so much
And the goal of
less
introducing merge
information.
sort now
I'm glad
is
you said that. This is when it'll start to get interesting.
And is obviously not less than 2, it's 8.
check your
excited.
watches.
This class are now in the L
So the goal of merge sort in my mind is that of the n log n sorts, I think it is one of the simplest to understand. It doesn't involve like a random pivot or something like that. It's like quick sort, and it also lends itself to a discussion of recursion, which at least in CS50 we don't have too many, I think, compelling opportunities to discuss beyond binary search. If we actually do that recursively, once we get to trees, we have an opportunity to talk about recursion, but it's really not until higher level courses that students, at least at Harvard, really tend to dive in deep to recursion. So this is one of those opportunities for us within CS50.
No, it is 2.
Do you?
so I have the
Is it
sort
intentional that you
on the right half. So here we go. Sort the left
remove
half.
the base that you essentially assume base 10 and
Dan
log
has
n,
step forward.
the discussion of log n?
It is. I mean, it's a constant factor difference. I could do log base 2 of n, but I worry that that level of detail just starts to scare all the more in terms of the mathematical notation and such. And I probably mentioned at some point, at least, the fact that there is only some constant factor difference between log base 2, log base 10, but for the most part, I just leave implicit what the base
Again,
is.
there's a key step here. What do I next need to do? Merge the sorted halves. Now we're going to just have everyone back and forth in this way because I kind of need some scratch space. It's almost like these guys are on a
And this is
table
the
and
key
I
to
need
tell
some
here that
room
initially
to
is not
move
obvious,
around.
though I do
So
just
I'm gonna
mention it,
merge you guys by looking
that
the left
there's
half
this trade-off,
and the
and this
right
is
half.
really thematic, I think, throughout CS50, whereby right now we've been stuck with an upper bound of quadratic time, of big O of n squared.
And now to merge the left half
But
in,
by spending another resource, in this case space, having what I described as some scratch space, or really just a secondary array that we can move people in and out of as needed when reordering, can we save on time? And so that's going to be thematic. If you spend some space, you can save on time, or vice versa. Sometimes it's development time, sometimes it's some other resource, but space and time are two of the most common ones.
You'll see that we got to this point of Luke and Darren by sorting the left half of the left half. Then we merge those sorted halves, which means the next step is sort the right
This is
half.
a tough one to see, whether it's with humans
All right, so
or
let's do
even
this more
with a
quickly.
graphical
All right, 6.
incarnation.
I'm going to claim you are now sorted.
And it's kind of a mind bend too. Like all you do is sort of half, then sort of half, then sort of half, then do nothing, and then suddenly it's sorted. But merging is ultimately the key
Merge,
step.
pretty trivial. So I'm going to merge in 6, take a step back, 8, take a step back, and now notice this is
Would
a
it be
useful
would it be
takeaway.
more clear
What
to
is now true
first
about the left half of the list, irrespective of how
break
we
them
begin?
into the
It is sorted.
essentially
Now,
the
it's not
pairs,
sorted in the big
so
scheme of things, but it is sorted
to be a little bit
independently
more
of the other.
strict
Now, what
about
step am I
following
on
the
if I keep
algorithm
rewinding
itself.
how
So
the story
essentially
began?
breaking them up into
Now I have
halves,
to sort the
and then
right
looking at the
half.
left
So
half,
now
and then
we're
breaking
way back at
that
the
up into
beginning.
Well, I did have
halves.
them step
Do this
apart
more
for that
rapidly.
reason,
So I'm
if
gonna
that's
sort
what you
the
mean.
right half
That's why
of
there
the
is
whole
this
list.
gap and a slight
What's the
gap there. I
next
can
step?
make more visible.
Sort the left half of the right half.
I see.
Sort
Okay.
the left half of the left half of the right half. And what's your name? Omar?
This is a hard one to
Done.
keep everyone on the
Left half
same
is
page.
sorted. Chris, take a step forward. You are
Because
now
you essentially
sorted.
have a
What's the key
mental
step now?
stack where you have to
Merge.
do
So
something,
one
do
is
something,
going
and then you
to
have to
merge
keep
into place here,
suspending
take a
what
step
you're in the
back.
middle of doing so that you can
3
recurse.
is going to take a step back, merge. So the left half of the right half.
This is an opportunity
now
to
sorted.
our earlier
Right, 'cause this
conversation
algorithm
about
feels like we are wasting
animations
way
and
more
such.
time than
I
before,
think
but if we did this in
we
real time,
will
we'll
soon
see
get
what the
around
takeaway's
to
gonna be. Now, here
making
I
our
am.
own sort of
Right
animation
half
of this
of the
that
right
moves,
half.
that tells
Let me
exactly
go
the
ahead
story
and
we
sort
want
the
to
left
tell.
half.
Because the humans here certainly add some undue complexity.
Ramsey is now
Even
sorted.
the
What's your name?
sound-based
Maria is now sorted.
visualization we
Take one
saw,
step forward.
you can really
Each
see what's
step
happening
here
with
is
merge
now
sort. Like there
merged.
seem to be these
I'm gonna plot
halves
for my
of
two
data
lists, left
being
and
merged
right.
together,
5 is gonna come
but you
first,
don't necessarily you don't see the
and 7 is gonna
merging
come next.
happening in
And again, this is
particularly
deliberate.
good
The fact that
detail.
they're taking steps forward and back is meant to represent
But what's
that we
nice happening
can't
here, and
do
the
this
reason that I
algorithm in place
ordered
as
the numbers
easily as
originally as I
bubble
had is so that we
selection
do
sort
see
and
the
insertions
even
are
numbers on
just
the left, the
swapping
odd
over.
numbers on the
I
right
literally
in
need a sort of
monotonically increasing
scratch
order,
paper
so that
in
the
which to put these
merging
files
really
while
is a
I do merging,
weaving in
and
this
then I can put them
particular
back in place.
example.
And that's key because I'm using
it's
a new
not quite
resource,
as random
space,
as
not just time. Okay, this is amazing.
it might
Left half
otherwise
is
be.
sorted, right half is sorted. Now that key merging step. How am I going to merge this?
And you really
So
see the
if you
merging
follow
now with
my left hand
lists
and
of this
right hand,
size.
I'm
And
gonna
I have
point
this
my left
common,
hand at the left
I guess, technique
my right
of
hand
using
at
my
the
left
right
hand and
half.
right hand as
Now I
often
have
as I
to
can
decide,
to
step by step,
explain
who's
what's
merging,
happening.
who
And
obviously
so
goes
I'm
first.
pointing at the start of each
Number one, so
list.
come on over
Now I'm
here. Here's our
hopefully
scratch
having
pad.
one come
So now
onto
number one,
his
and notice what
location
I'll
in
do
my
with my
so-called
right
scratch
hand.
space.
I'm gonna
Now all
move
I have to
my
do is
right
move
hand
my
one
right
step
hand over one
over
spot.
to point at number
You're
3,
doing
and now I
exactly
have
the
to make
same movements,
decision.
and in the same
that's right
outfit.
in
It's
front of
just
Luke here.
it's
Good?
just too.
Oh, I
it's
am.
too
Yeah.
funny.
Wow. That really is
Comes next.
ingrained.
We have Luke with number 2.
That's good. That's effective.
You did the
That's-
same thing with the hand, a little like rotating.
That means it's
hand.
effective.
Number 2, so
Is
you
it-
come
does it?
here.
It does.
Left
Or does
hand
it mean
now
you're set in
is
your
going to
ways?
be incremented
No, it
to
means
point
I am
down.
learning
And
from
here's the key takeaway with
myself.
merging. I'm going to keep doing this, obviously, if you kind of follow the logic, but my hands are never going to go backwards.
And this is the
Which means
key
I'm
to
only
emphasizing
ever
that the
moving to
merging
left
step
of my merging
is a
process.
linear process
That's gonna
here,
be key to our
right?
analysis
I'm
of
really
this goal.
only
So now let's finish this up rapidly.
advancing my
3 comes
hand
next.
to the right. I never
4
double
comes
back.
next.
And so therefore, if I have to point at
now 5
everyone,
comes
and
next.
there are n such
That's 6.
everyones, I'm doing this n
7.
steps in total.
And then finally, 8. Feels like the slowest algorithm, but not if we actually run
Sorry,
it
folks,
at
took me
the
a while
same
to
sort of clock speed, so to
explain
speak,
this
the
one.
Same ticking clock as before. Why? Well, let's take a look at the end result.
Okay, so now
Let's
we're
go
going to take
back
a look
over
on the
here.
overhead.
Yeah,
Let me
we
pull up
yeah, you
a
just said that.
demonstration visually.
I'm explaining what's
just
going
did.
on.
Zooming in here.
So this is another demo, Java applet for some reason. It's nice in the end. You gotta approve the security warnings. I then have to zoom in so it fills the screen. I have to configure each of the things, and then I have to rapidly click on all 3 demonstrations so that they start roughly at the same time. But what's nice is you see bubble selection sort and merge sort side by side, and hopefully, given random inputs, you'll really feel the difference of n log n versus n squared.
Not only visually, watch just how much more efficiently this leveraging of division and conquering can be when applied to a data
And it's funny,
set
I've on
that's
occasion
not even
used this
8
as like the very
size-
last thing in a
size
class
8,
where
but
we
even
end on
much,
this note and
much
you get these
bigger.
like ooh ahs. And it's funny because it's just like people getting excited over a sorting algorithm, but it's a good cliffhanger if you introduce this first, for instance, And you'd hear a lot of like oohs and ahs right now, I'm sure, if we had the audience mic'd. But this is a good cliffhanger, I think, for the end of class. Depending on the order in which you present the materials or the pace at which you're going, I could certainly imagine in a compelling way ending one class here, kind of like we did with the first part of week 3, but doing the audio versions of it, the YouTube video, so as to motivate the next class with how did we do so much better.
Choose bubble sort, and just for kicks, let's choose insertion sort, just for good measure. And this time again, let's choose.
This might be a
merge sort.
result of mine not hearing any oohs and ahs, so I
side
thought we'd try it again and see if it works the second time.
And it's not, in fact, a fluke. What I've effectively done.
Proof by
is
2
I've
examples.
divided
Yeah.
the input
Great.
in half, again and again and again. And there's only so many times you can divide your input into halves, left and right. What's the formula that we keep seeing that describes the division in half?
Look at that, everyone's attention still up there.
Log n.
Amazing demo.
But then there's one other key step. This algorithm
Look at that
is not
engagement.
log n steps. If it were only log n steps, we would be in the same problem as before, where we can't be sure everything's sorted. You have to minimally look at n elements to be sure n elements are sorted. Otherwise, it's a leap of faith. So it's minimally log n steps. But what about this key merging step, where I merge my left
This is
half
the hard
and
part for
right
me
half
always to
and walk
explain.
across the stage?
And my own approach to these explanations has varied over the years, where once upon a time I took a very mathematical approach. Nowadays I take a much, I hope I take a more intuitive approach. Sometimes it's a more visual approach. But I suspect the reality is for each person, this kind of idea clicks in a different way. And so we generally present all 3 of those techniques nowadays: a bit of math, a bit of visualization, and a bit of logic or intuition.
What might be now the upper bound on the running time of our algorithm? N log n. And indeed, that's what we've achieved here. So the feel that you see visually when those 3 things run side by side
And
is
a helpful
n
intuition, I
squared
think, when
against
presenting
n
n
squared
log n
against
is that
n log
even if a student doesn't really know what log n is, and that's kind of the scary part of this expression,
much faster.
n squared we've generally concluded is bad or slow. It's not ideal.
Turn here today,
But if log n is less than n, then n times log n is surely less than n squared.
You lost me with that. I just stopped listening. Sorry.
That's
I was
okay.
so excited by seeing the end of the lecture.
The lecture? Yeah, that was a cliffhanger.
So here we have Colton again.
Doing a performance, yep. So he'll often start class this way. We don't capture the beginning performances as people are coming on in, but he then shoots these studio performances so that we have a canonical version of it. Very mesmerizing, though. And what's been nice, indeed, is that at the end of the semester we have a couple of events, one of which is the CS50 Fair, and more recently we had CS50 hackathons in a couple of different cities. And so the fact that we have this corpus of music that are either covers or his original works means we actually can bring something musical to these events. And it's been nice background music, it's been nice foreground music for certain parts of these evenings. So it's actually been a nice way of tying the semester together and giving students this sort of, hopefully for some of them, this sort of emotional reaction where they remember that's how the class began and now we're ending the semester in the same way. And it's also just fun. I mean, a non-trivial number of students have taken a technical interest in how all of this works and chat with Colton after class or at the fair or the hackathon or the like. And indeed, all of this is ultimately driven by software, since that's just this USB cable talking to his computer where he programs everything. It's an interesting art form. And he got more into it by week 3 with the hand gestures too.
I remember the last one just seemed to be so involved
Yeah.
that he didn't really seem to have time. Prior ones.
I wonder when he does that how many buttons he's actually hitting. I can't quite tell.
I think it's one because he can
Just one,
code
but
both
then he spins
the
his hand.
sample, which can be multiple seconds.
But I just
And,
mean the colors kind of spin.
Oh yeah, that can be, that's programmed as part of the
It's a cool
the
effect.
MIDI file he was saying.
Incoming call
So this is a bit.
from Metro. No.
I think the first time I saw this, I was like, what is you took a call during the performance? I wasn't really paying close attention to the lyrics.
Drop it.
This would make a great Apple ad now, though.
Yeah. phone, just over there on the right.
I don't know how he remembers all of these patterns in these keystrokes. Oh, not short song. I'm having trouble remembering my scales on a piano.
Maybe that's your problem.
I'm just not capable of this.